Okay. So let me just share a Microsoft whiteboard. Uh, so then we can.
Sir, it doesn't get recorded actually. Microsoft Whiteboard.
What?
So Microsoft Whiteboard does not get recorded on Teams.
Who said? I have been doing it since last one semester.
Sir, in the previous semester we had this for course CML 103 taken by
But
Professor Shashankdeep. So in that case, it didn't record Microsoft Whiteboard.
I used to record it on the Microsoft whiteboard itself. Can you see it?
Yes, sir.
No.
This one it works. Yes, sir. This one it records. The one on Teams inbuilt one that doesn't work.
That I never use. Inbuilt one I never use.
Yes, sir. Yes,
Okay.
sir. This will work. Thank you, sir.
Okay. So please go through the problem statement. Okay, so the first problem is a wall has two layers of insulation on it. The layers are of equal thickness, but the thermal conductivity of layer 1 is twice that of the layer 2. How much more thicker should layer 2 be if the heat flow is to be reduced by 20%? The total and the driving force remaining unchanged, what would be the fractional reduction in the heat flow if the material of layer 1 is replaced by the material of layer 2? Question 1. Okay. So what is being given to us is there is a composite wall which has two layers, layer 1 and layer 2. So maybe I just draw a so let's say this is 1 and this is 2. Okay, layer 1 and layer 2 both has the length L, the thickness of L, isn't it? And what is being given again is this is, let's say, K1 and this is K2. What is been given is how much more thicker should layer 2 be if the heat flow is to be reduced by 20%. Okay. Now again, area you can assume as 1 meter square, let's say, and what is been given is K1 is given as K1 is equals to twice K2. Okay. Now if we assume that the length is same, then the rate of heat transfer Q can be given as the rate of heat transfer Q can be given delta divided by L by K1A plus L by K2A. Okay, this is the equation, correct? This is the same equation what we have derived in the last class. This is the same equation what we have derived for the composite slab the last class. Are you all with me? Hello. Are you all able to
Yes, sir. Yes,
follow?
sir.
Yes, sir.
Okay. Now what is been given is how much should be the layer 2 thickness in order to reduce the rate of heat transfer by 20%. So when the layer, both the layers are having the equal length equals to L, in that case this is the equation, isn't it? Now this is the condition 1. This is the first condition. Second condition is what is been given is, in second condition it is given that the rate of heat transfer has to be reduced by 20%. That means how much will be the rate of heat transfer? Rate of heat transfer will be 0.8 Q. Correct. Again, the temperature difference is going to remain the same. That is what is been given in the problem statement. If you read through, that is what is been given, isn't it? The total wall thickness and the driving force remain unchanged. Driving force remain unchanged means delta T remains unchanged. Okay. Again, total wall thickness remains unchanged. That means the total wall thickness, which is now that is twice L. That twice L is going to remain same. But internally, this boundary between these two layers is going to shift. Okay. So how much this boundary between these two layers should be shifted in order to have 20% reduction in the total heat rate, the rate of heat loss. That is what is been asked. Now let us assume that the thickness of the layer is, let's say, X. So maybe I just write down the new thickness of layer 1 is, let's say, X. Correct. So what will be the thickness of layer 2? Therefore, thickness of layer 2 will be equals to 2L minus X, isn't it? Because the total length 2L is going to remain unchanged, isn't it? That is what is been given in the problem statement. So this equation number 1 for the new condition, this is the original condition. New condition is this. So for new condition, what we have to write down is this will be X divided by K1A. Remember what is been given in the problem. Again, what is been given is in the problem, what is, let me just write down the same thing, then probably we will change K1A plus 2L minus X divided by K2A. So this is the new equation. In addition to this, what is been given is the thermal conductivity of layer 1 is twice the thermal conductivity of the layer 2. That is what is been given in the problem statement. If we go back and see, the thermal conductivity of the layer 1 is twice that of the layer 2. That is what is been given. Correct. So that means equation 2 can be rearranged again further. So what we can write down from equation 2 is 0.8 Q is given as delta T X divided by 2K1A, sorry, 2K2A plus 2L minus X K2A. This is what the equation is. Okay. And from equation number 1, what we can write is from 1 we can write is Q is given as delta T divided by okay. Now from 4 we can directly, from 3 and 4 what we can write is we can take the ratio of these two. What we are going to get is from 3 and 4. From 3 and 4, if we divide equation 3 and 4, what we are going to get is 0.8 remain as it is. Delta T will get cancelled out, and this area will get cancelled out. L is going to be there, so this is going to be L by 2K2 plus L by K2 divided by so again K2 can be cancelled out. So what we are going to get is L by 2 plus L divided by X by 2 plus 2L minus X. And if we rearrange this, what we are going to get is we can get the relationship between L and X, isn't it? So what we are going to get is X is obtained as 0.25 L. So are you all getting the same? Hello?
Yes, sir. Yes,
So
sir.
what it means? What it means is if we reduce the length of the first layer by 75%, then my rate of heat transfer is going to reduce by 20%, isn't it? Correct? So what it implies is in order to reduce the heat loss by 20%, the thickness of layer 1 should be decreased by 75% and the thickness of layer 2 should be increased by increased by 75%. So this is the answer of first part. This is the answer of first part. Correct. Now in the second part, what is been asked in the problem is, in the second part it is asked that what would be the fractional reduction, what would be the fractional reduction in the heat flow if the material of layer 1 is replaced by material of layer 2. The second part of the question is, if I go back here and read through, what would be the fractional reduction in heat flow if the material of layer 1 is replaced by the material of layer 2. So what is been asked in the second part is, if this entire slab is made up of, let's say, layer 2 material, how much will be the reduction in the heat loss? That is what the question is. Correct, isn't it? So that also, for this third condition we can write down. For this third condition we can write down further. So what is been given in this third condition is the layer 1 is replaced by layer 2, isn't it? So let's say the heat transfer is, let's say, Q dash. Again the driving force is remains same, so delta T remains same. So we can write down the equation as delta T remains same, and the resistance in this case is going to be 2L by K2A, isn't it? Because the entire layer 1 is now replaced by layer 2, isn't it? So we will have only K2. Area of the cross section remains same. The thickness of the complete slab is now going to be 2L, because both layer 1 and layer 2 are made up of the same material as of layer 2 now, isn't it? And delta T, which is nothing but the driving force, remains as it is. So this is, let's say, equation number 5. Now again, if we divide equation number 5 by equation number If we divide equation number 5 by equation number 4, then what we get is okay. So Q dash by Q if we obtain. So this delta T will get cancelled out, and what we will have is L by 2 K2A plus L by K2A, and this will be divided by 2L by K2A. Correct. So this K2 will get cancelled out. So what we will get is L by 2 plus L divided by 2L, isn't it? So this becomes 3L by 4L. So that becomes 3 by 4. So what it means is if we replace this entire material by the layer 2, if the layer 1 is completely replaced by layer 2, in that case the rate of heat loss Q dash is going to be 3 by 4 times Q. 3 by 4 times Q. So that means what? The heat loss is going to reduce by 25%. So this is the second part, answer of the second part. So is it clear to everyone?
Yes, sir.
Yes, sir.
Okay. So now can we go to the second question? If it is everybody is
Yes,
okay?
sir. Yes, sir.
Okay. So now what is the second question is? Second question is here. Okay. So a hot chamber has an 8 centimeter thick inner layer of fire brick. Thermal conductivity is given 1.04 watt per meter degree Celsius, and a 30 centimeter outer layer of ordinary brick with thermal conductivity of 0.69 watt per meter degree Celsius. The inside and outside surface temperatures of the composite wall are 400 degrees Celsius and 75 degrees Celsius respectively. Considering that the outer surface temperature is too high, it is decided to apply a 5 centimeter thick layer of plaster on the outer surface. On doing this, the outer skin temperature is reduced by 60% and the rate of heat loss decreased by 250 watt per meter square of the wall area. Calculate the thermal conductivity of the plaster layer. Okay. So now what is been given in the problem is there is a composite wall, isn't it? So there is a hot chamber has a 8 centimeter thick inner layer of fire brick, isn't it? And outside of this fire brick there is a ordinary brick layer. Thermal conductivity of both the layers are given. Again, temperature inside the furnace is given. Composite wall are given. That is 400 degrees Celsius, whereas the temperature outside this ordinary brick is given, which is 75 degrees Celsius. Now this 75 degrees Celsius temperature which is outside of this hot chamber is considered to be high, and therefore again a additional layer of uh, plaster is added. Okay. By adding this additional layer of plaster, the heat loss is reduced by 250 watt per meter square, and also the outer temperature is reduced from 75 degrees Celsius to 60 degrees Celsius. Okay, isn't it? So now the question is what is the thermal conductivity of the plaster layer if the thickness of the plaster layer which is given as 5 centimeter. If the 5 centimeter thickness is the layer plaster layer thickness, then what will be the thermal conductivity? That is the problem. Now in this particular question, what is been given is, let me just write down the equation again. So question 2, let me just write down question number 2. Okay. So what is been given is Q is given as delta T. So in this case, delta T is what? The outer temperature was inner temperature was 400 degrees Celsius minus the outer temperature was 75 degrees Celsius. So that is delta T divided by resistances of both the walls. So there is a fire brick. So the thickness of the fire brick is 8 centimeter. Thickness of the fire brick is 8 centimeter. If I am not wrong, yes, 8 centimeter and 30 centimeter is the ordinary brick. So that becomes 0.08 divided by K1A. Maybe I just write down this in terms of actual temperatures. Okay, so let me write down in terms of actual temperatures. So this becomes Ti minus T naught divided by L1 divided by K1A plus L2 divided by K2A. So this is the equation. So we can simplify this as 75. L1 is 0.08 divided by K1 is 1.04 and area we are assuming 1 meter square. So that becomes 1. The thickness of the ordinary brick is 13 centimeters. So this is 0.13 divided by thermal conductivity 0.69. So by doing this calculation, calculate the Q. What is the value of Q? What is the value of Q? Anybody? Hello? Can anybody tell me what is the value of Q?
Yes, sir. It is 124.89.
Okay. 1225 watt. Something
Yes, sir.
around this you should get. Correct?
Yes, sir.
Okay. Now what is been given in the problem is new plaster layer is added. Plaster layer is added. New plaster layer is added. And by doing this, what is happening is Q dash is obtained. So Q dash is nothing but Q minus 250, isn't it? So that becomes 1225 minus 250, isn't it? So this becomes 975 watt, correct? And also the temperature, is reduced. T not new is reduced to 60 degrees Celsius. Correct. So now we can write down the expression again. So Q dash is given as Ti minus T dot new divided by L1 by K1A, L2 by K2A plus L3 by K3A. So this is the same expression which we have derived for the composite wall, isn't it? So we can now put all the values here. So Ti is again same. So 400 minus T naught new is nothing but 60 degrees Celsius. So that becomes 60 divided by L1 is the same 0.08 divided by 1.04. The second layer is again the thickness is 13 centimeters, so 0.13 divided by 0.69. Area is again assumed to be same as 1 meter square. L3 is 5 centimeters, isn't it? 5 centimeter is given, isn't it?
Yes, sir. It is 5 centimeters.
Correct. So 0.05 divided by K, and this should be equals to 975 watt. So the only unknown in this equation is K, isn't it? Only unknown in this equation is K. So K is obtained as K here in this case obtained as anybody. K comes out to be?
So just solving once.
Yes.
Sir,
Is it clear what we are doing? Anybody? Anybody is having any doubt?
it's around 0.6, 0.599.
0.6. Correct. 0.6 watt. So this comes out to be 0.6 watt per meter degree Celsius. Okay. So this is going to be the thermal conductivity of the plaster layer. So this will be the thermal conductivity of the plaster layer. Okay. So this is the answer of the second part, the second question. So this is all about the tutorial 1. So we have only included these two simple problems in this tutorial. Problems are going to be more complicated in the upcoming tutorials. We are just starting, so the simple problems are done. So is there any question so far? Hello?
No, sir. So far it is clear. Sir, just one question, that why did we assume unit area in both the cases? Like it's
So
not given. So
otherwise you will get all your answers per unit area, isn't it? That's it. If you don't assume, you will get all your answers per unit area.
so that's something we have to assume by default. So that's allowed, right?
Yes. Otherwise it is specified. Okay. If you don't assume, we will get the answers. Q will be obtained as per unit area. So if it is nothing is given, you can assume per meter square the cross sectional area. Otherwise,
Okay,
mostly it is specified. Okay.
thank you, sir.
So can we stop here? Can we stop here unless you have any doubt, any question to ask?
No, sir.
Okay, then see you on Thursday then.
Yes, sir. Thank you so much.